On the left side of this split screen, we see a standard direct current, or DC, system. Voltage and current are constant, so calculating power is as simple as multiplying the two flat lines to get a constant rectangular area. On the right side, alternating current features sine waves that don't always align. Watch the specific regions where they fall out of sync. Multiplying a positive voltage by a negative current drops the resulting product completely below the zero axis. That negative area represents something physically impossible in a basic DC circuit: power flowing backward. Energy is actively returning to the power source. If we blindly multiply the raw peaks of voltage and current like we do in DC, we'll overestimate how much energy the circuit actually dissipates. The mechanism behind this temporal misalignment is the phase angle, represented by the Greek letter phi. It measures exactly how far out of step the voltage and current signals are from one another. Because AC systems vary in time and temporarily store energy, calculating true power dissipation requires a different mathematical approach than standard DC models. To measure the actual energy transferred in an AC system, we cannot rely on instantaneous spikes. We must derive the average power over a complete, full cycle. Our destination is this specific equation: average power equals root mean square voltage times root mean square current times the cosine of phi. That final term, the cosine of phi, is known as the power factor. It is the critical variable introduced by alternating current. Defining the physical reality of the power factor allows us to determine the actual work a circuit performs. Starting top left, we multiply the sinusoidal functions for voltage and current, incorporating the phase difference phi, to get our baseline formula. Applying the product to sum formula, we expand that initial equation into the middle boxed form. Notice how this expanded equation splits into two distinct halves. On the left is a constant term based on the phase angle. On the right, a time-varying term based on frequency. This graph plots that time-varying term. Over one full cycle, the positive shaded areas above the zero line are perfectly mirrored by the negative shaded areas below it, resulting in a net value of 0. Since the time-varying term averages to 0 over a full period, average power is dictated entirely by the constant term, cosine phi. Replacing maximum voltage and current with their RMS equivalents finalizes the formula. This proof demonstrates that average power dissipation depends equally on the cosine of the phase angle and the raw magnitudes of voltage and current. This phasor diagram maps voltage and current separated by angle phi. Projecting the current yields I cosine phi, the active component. Running parallel to voltage, this fraction performs real work. The orthogonal projection gives I sine phi, the wattless, idle component. Being 90 degrees out of phase, it does zero net work, merely shuttling energy back and forth into magnetic fields without yielding net power dissipation. Alternating current is a superposition of working and idle current, strictly dictated by the phase angle. We must identify what physical properties dictate the size of this phase angle. This impedance triangle maps a circuit's resistance. The base is resistance, vertical is reactance, and hypotenuse is total impedance. This internal angle phi matches our phasor diagram. In the top left equations, the power factor, cosine phi, is the ratio of true resistance to total impedance. The power factor is controlled by the physical hardware ratio, resistive material versus reactive energy-storing components. This creates a hard geometric limit on system efficiency. We can test the robustness of this model by applying it to theoretical boundary conditions, starting with a purely inductive or capacitive circuit where no true resistance exists. In the right column, marked Case 2, we see the mathematical outcome. When resistance equals 0, the phase shift is exactly 90 degrees, driving the power factor to 0. In this state, 100% of the current becomes wattless. Zero power is dissipated regardless of the raw current or voltage magnitudes. Contrast this with Case 1 on the left, a purely resistive circuit. With zero reactance to shift the phase, voltage and current align perfectly. Impedance equals resistance, and the power factor hits its maximum limit of 1. To maximize real power output in any AC system, engineers must minimize the reactive components and drive the power factor toward 1. This brings us to the optimal condition, the series LCR circuit operating exactly at its resonant frequency. Under case 3, at resonance, inductive reactance exactly equals and cancels out capacitive reactance. The entire impedance formula reduces so that total impedance equals true resistance. Watch this impedance triangle. When the reactances balance out, the vertical side of the triangle shrinks completely. The hypotenuse drops down to lay perfectly flat against the base. Because Z equals R, the ratio becomes R over R, dropping the phase angle to 0 and maximizing the power factor to 1. The AC equation now mirrors the optimal DC formula, showing power is dissipated strictly through the resistor. Tuning a circuit to resonance forces energy-storing components into equilibrium, eliminating wattless current to achieve maximum power transfer.